Okay, so previous lecture we looked at the cross point complexity for a closed network, but that is a very ideal scenario. Okay, that is basically we know the value after which if the number of middle stage switches are grown up, then it will lead to strictly non-blocking property. But as I actually have explained earlier, in real life situation we do not want to build up strictly non-blocking switches, we actually build up blocking switches. In fact, we do two things, we either build only the blocking switches and use them to reduce the cost because certain amount of blocking is acceptable, or we do create a strictly non-blocking switch and then introduce blocking by using concentrator units. That basically means I am going to have a special kind of switch where number of inputs are large, number of outputs are small, use a strictly non-blocking switch and connect to the large one. So, I have introduced a blocking by use, this is known as concentrator unit, okay, and that is a switch. This configuration also has been used in lot of telecom switch implementations, okay. So, in fact, most of them actually were using this. So, if I am going to actually do not satisfy that condition of 2 into m minus 1, those many number of middle stage switches is going to be less than that, what will be blocking probability. So, that question actually remains. So, if you have a switch like here, so it is a 3 stage closed network, now one important thing is that I want to set up a connection between two free incoming and outgoing port. There are other switches also here which you should ask question what is going to happen with those, how those will be incorporated. But now you take any pair, you take this pair and this pair, this is independent of when you set up a connection between these input output port pairs, because these links these are known as input links, these are output links, that is a totally different set when I am considering these input and output ports. Okay. So, the blocking here will only be dependent on the availability of a common link, a free link has to be available here and a free link has to be available here. Whether this link is available or not, or this link is available or not is immaterial. So, those need not be accounted for, and the situation you take any pair, the situation is same. So, whatever blocking probability which I will estimate for these two is going to be true for any other possible pair. In fact, that is a premise which we use to estimate the blocking probability. So, but we do know if my number of middle stage switches, if this is, these ports are m, these ports are m, the moment it is greater than 2m minus 1, it should become 0. That is what the clause theorem actually says. We actually have seen this in the previous lecture. Now, how to estimate it here? So, there are actually various ways. So, we will discuss two of them. So, one is the Lease approximation. Okay. So, this is very simple and trivial exercise, this is not a great deal. So, the call arrival rate we define as A, the probability that this link will be active or a call will be coming up. Okay. So, if this is m and these are k number of links, k are the middle stage switches and it is a closed configuration. So, what is the probability this link will be occupied is a very simple calculation. So, which actually means there are m number of ports, each one of them can be occupied with probability A. This should be equal to the probability of any one of these link getting occupied, that probability is P we call it. So, P should be equal to, yeah, let us call it this way. So, P should be that probability that any one of these links will get occupied is m a by k, and k is larger than m, so this is going to be smaller. See, I am not assuming that blocking is happening because of this switch. This switch, the blocking will happen, remember the m by n composite switch, when n is m by n composite switch was something like this. When this n is smaller than m, then blocking happens here. If n is greater than or equal to m, there is no blocking. The condition here is k is greater than or equal to m. Okay, this even can be even larger. In fact, this Lease approximation gives you an estimate, okay, but this still says the blocking is going to happen when it cannot happen. When your k is going to be 2m minus 1, the formula will still tell the blocking is going to happen. So, this is a probability that this link will be occupied, okay. And similarly, I can estimate what is the blocking probability, what is the probability that this link will get occupied, this will also be p, this is m. So, call which is coming here is going to have an impact connecting to any one of the outgoing ports. So, effectively when I am looking at the probability that a call will be coming here, the arrival rate, that is because of all these. So, this should also be A. I am looking at a complete symmetric condition, any input is trying to connect to any output with equal probability. Under those symmetric conditions, both side it is A. So, this occupancy probability will also be, so this is here is k, will also be given by m a by k. Now, the probability when the blocking will be happening, when you cannot find out a path. Now, how many possible paths are there? You can actually route through this, you can route through this, you can route through this. There are k such possible paths. And when a path is not available or blocked, when this is being used to make a connection to somebody else by some other busy port, so this is occupied, even if this link is free, you cannot use this path. There is a possibility that some other output port from here takes this and connect here, so this is occupied. Even if this is available, you cannot use this path. There is a possibility that some input here is connected to some other output here and both of them are occupied. You can always set up a connection between them only when both input and output, both links are available. So, essentially we have to find out when the links will be available. So, when this a path will be busy, a path will be busy either when both of them are busy or one of them is going to be busy, or 1 minus that both of them are available. So, the both of them are going to be available. So, this is the occupancy probability of a link. This link is not being occupied, that probability is 1 minus p. This link is also not occupied, is 1 minus p, so I will say 1 minus p square is the probability that this path is not occupied and can be used. Okay. So, 1 minus this should be means the path is going to be occupied. This essentially can happen because this is busy or both of these links are busy. So, all three are being now taken here. So, remember this is nothing but equal to that both of them are busy, which is going to be p square plus this is busy and this is not busy and this is busy, this is not busy, which will be 2 into p into 1 minus p. So, remember this both are same. So, I have just computed it in the other way around. So, this is the probability that this path is busy. Now, if all the possible paths, all of them, all k of them are actually occupied, then you cannot set up the communication between this and this free input and free output port. So, that is what is going to give you a probability of blocking. Remember, this is a switch being in blocked state, this is a time congestion, this is not a call congestion, this is a probability that switch is in the blocking state. Okay. So, this is what is known as Lease approximation, and of course, I can replace P by this. So, it will become 1 minus now the problem is, if I actually put k is equal to 2m minus 1, this should become 0, but that does not happen. You can compute this, or any value which is higher than this. You take any value of m, compute, take some value of a which is a probability, can take value from 0 to 1. This is not going to be 0 in this case. So, this start deviating actually, this start deviating for larger numbers, but is a good approximation if my k is, and if we are doing randomly the things, then this is going to be a good approximation. Okay, but this is still an approximation, it is not the exact value of probability of blocking. And I think the mistake is that the probability that the call blocking will happen, that depends on the switch state, we have not taken that. So, I think we have to modify this approach. So, modified approach was given by Carnot. So, there is a Carnot's approach which will give you more exact blocking probability, but this blocking probability will be call loss probability. So, we will actually represent this switch by some state sigma, and then there is going to be call arrival probability which is because of sigma. Okay. So, in fact, so arrival probability which was sigma, probability that your switch is in sigma state, and the probability that call will get lost when you are in state sigma, and you sum it up over all possible states, and these are all the calls which will be arriving. This will give you PL, the call loss probability. And interestingly, this call loss probability and corresponding the switch being in probability of switch being in blocked state or time congestion, they are also related by the same relation which we have derived earlier. So, next lecture we will be looking into the Carnot's approach, Carnot's approximation for finding out the call loss probability.